Have you ever really looked at an old railroad tie and noticed how it splits right at the ends? Or wondered why an I-beam has that very specific I shape? Well, that's not just a coincidence, and it's not random. They are answers to a powerful, invisible force that's always trying to slice things apart. So today, we're going to pull back the curtain and make that force, known as transverse shear, visible.
You've probably seen this a million times and never gave it a second thought. An old railroad tie, weathered and worn, with these deep cracks splitting open right near the ends. It looks like it's just rotting away, right? But it's not random at all. It's actually a clue, a breadcrumb trail left by an incredibly powerful force at work. I mean, really, why there, specifically? What is actually happening inside that chunk of wood every single time a train rumbles over it?
Well, the answer is a very specific kind of internal stress. The culprit behind these cracks has a name. It's a force called transverse shear.
Okay, so just think of that railroad tie as a simple beam. When a huge load, like a train wheel, pushes down on it, the beam doesn't just bend. Something else is happening deep inside. There's this massive internal force trying to slice it vertically, like a giant invisible pair of scissors trying to snip right through it. That, right there, is the essence of transverse shear.
So if we want to get a little technical for a second, what we're talking about is transverse shear stress. It's the stress that acts perpendicular, or transverse, to the long part of the beam. It's basically the material fighting back against that invisible slicing action we just mentioned. And believe me, it's happening right now in just about every load-bearing beam all around you.
I know. Slicing forces inside a solid object? It sounds kind of weird, right? It's tough to really picture. So let's use a really simple analogy to make this whole invisible stress, well, suddenly visible.
All right, check this out. Imagine you just stack a few wooden planks on top of each other and try to bend them, like you see on the left. They slide past each other pretty easily, no problem. But now, look at the picture on the right. If we glue those same boards together, they bend as one solid unit. They become so much stronger. And why? Because the glue is physically stopping those layers from sliding against each other.
That stickiness, that internal force preventing the layers from sliding, actually has its own name. It's called longitudinal shear stress because it acts along the length of the beam. Now, you might be thinking, hang on, I thought we were talking about the transverse or slicing force. And you're absolutely right, but here's the incredible part. The two are directly connected.
And here's the crucial link, the big reveal. You can't have one without the other. Think of a tiny little cube of material deep inside the beam. For that cube to stay stable and not just spin out of control, the vertical slicing forces on its sides have to be balanced by horizontal sliding forces on its top and bottom. It's a fundamental property of physics. The external slicing force creates an internal sliding force. They're a package deal. And that's the reason those railroad ties split right along the grain.
So, understanding this is really cool, but for an engineer, seeing isn't enough. They need to be able to predict this force, to control it. And for that, they have a really powerful tool, the shear formula. Now, don't be intimidated by it. Just think of it as a recipe for figuring out the stress inside a beam. And here is that tool. Tau equals VQ over IT. Don't worry about the symbols just yet. What this little formula does is give us the power to calculate the exact shear stress at any point inside a beam so we can design things that are safe and efficient and don't fall down. Now, let's pop the hood and see what each of these parts really means. Okay, let's break this down real quick. V is that slicing force, so think of the weight of the train wheel. I is all about the beam's shape and how well it resists bending. T is super simple. It's just the thickness of the beam where we're measuring. And Q, well, Q is the secret ingredient. It's a value that measures how much of the beam's area is trying to slide at a certain point. The bigger Q gets, the more that sliding action is happening and the higher the stress. This is why the stress isn't the same everywhere inside the beam.
So that's the theory. Now let's see how this one formula scales up from a single beam to the very structures that define our skylines. This is where engineering really turns math into reality.
Hey, remember our glued boards from earlier? Well, this is the exact same principle, just on a massive scale. These little metal nubs are called shear studs. They're welded to steel floors before concrete gets poured over them. They act like super strong glue, locking the concrete and steel together so they can't slip. It forces them to act as one incredibly strong composite unit, and it's all thanks to managing shear stress.
And what about the most iconic shape in all of construction? The I-beam. That shape is no accident. It's a masterclass in efficiency. The wide top and bottom parts, the flanges, are put way out there because that's the best way to resist bending forces. But the thin part in the middle, the web, it has a totally different job. It's designed specifically to handle the shear forces, which, thanks to that Q value in our formula, are always strongest near the center of a beam. It's just brilliant design, putting the material exactly where it needs to be.
Now, as powerful as this formula is, we have to be honest, it's a simplification. It works incredibly well for long, uniform beams, but it gets a little less accurate for really short, wide beams or right near sharp corners where stresses can concentrate in weird ways. You know, a key part of engineering isn't just using the tool, but knowing when it's the right tool for the job.
So the next time you look at a skyscraper, a massive bridge, or even just a simple wooden shelf, remember what's going on inside. There's a silent, internal battle being waged against these forces of slicing and sliding. Our entire built world relies on engineers winning that battle every single day.
We've made one invisible force visible today. So the next time you cross a bridge or look up at a skyscraper, you'll see not just steel and concrete, but a delicate balance of hidden forces. It really makes you wonder, doesn't it? What other secrets are holding our world together, just waiting to be seen?